Okay, so let's first talk about the TENNs-PLEIADES algorithm. Okay, this is mentioned by Xiaoming in our previous. So what is it? First, let me pay attention to who wrote this paper. Okay, so it was written by Pei and Koinen. Okay, who are they? They are two researchers at Branch. And what is Branch? It is an Australian IC design house focusing on AI edge chip. And what is their claim? They claim they developed a new spatial temporal convolution kernel. So what is it for? So since there are, for example, there are several threads. This is a video. And if they have a better convolutional kernel, they can convolute several images. Then they can use the convoluted result to predict some actions in the video. And what's their claim? They claim their new convolution kernel can convolute more frames compared with existing convolution kernel. They can only convolute with less frames. Their performance is better. Okay. So they test their algorithms on 3 datasets, the IBM DVS128, Prophecy, General 4 Rosin. Okay, so let's take a look. What are they? So what is the 128 hand gesture dataset? It was created by IBM, and it was a paper published in CPR 2017. Okay, take a look what it is. So what is DVS128? It is a camera. And it is a camera developed by a company called Innovation. Okay, and the resolution of the camera is 128. So this is why it is called DVS128. There are several different models, and IBM, they provide the true nose processor is this chip, and they can use the board. This is NS1E developed board to connect the board to the camera, and they can use their processor to do edge processing. It means you don't need a laptop. You just use the board and the chip and the camera. You can calculate some to predict some actions in the video. So let's take a look. What does the video looks like? So you can see there is a subject. He is moving around, and it will create a video, but it is not an RGB video. It is an event video. Event video means, so take a look of this. Suppose there are something moving, okay, then the RGB camera, it will generate a frame, another frame, frame by frame, okay. So you can see that it is moving, the black circle is moving around. But the DVS camera, it will generate only the difference from this frame and this previous frame. So when the black circle is moving, you only see it is go in the place is changed. It's only the around this circle. So what is the advantage of this type of camera? The benefit is it is more power efficient. Okay, and the second, the frame rate can be pushed very, very high. And the third, because it only generates the signal of the difference on the pixel, so the throughput is also improved. Okay, so let's take a look of this video. This, as I say, the camera is developed by the Innovation company. So this video is cropped from Innovation's official website. So let's take a look. Okay. As you can see, there is a runner, and the camera only capture. Okay, so that you see the black. Black means there's nothing changed, and there's white and yellow. Blue. The blue means there in a sense there's something. Okay, the brightness is greater than its previous frame, and the yellow white part is the brightness is weaker than its previous frame. Okay. So basically you only see the changes occurs around the runner and and across the road. Okay. Otherwise, there's no other change occur in the frame. So the event data looks like this. The dimension is 128 by 128, and then there are many frames. When the subject moves around his hand, we only see the change on some frame. So when we take this frame out, it will look like this. And you see two different colors, the pink and the green ones. Okay. So when his arm moves to another position, you will see the change on those pink and yellow, pink and green points. Okay, so that's their experimental result. The convert 1 plus 2D was there. I say there is mean the pi and coeval use participant in the competition as 2024. Okay. And this is their new algorithm. The change only occurs on the new convolution kernel. So the accuracy improved from 99.17 to 100%. Okay. Second data sets they tested. As you can see, this is a eye tracking data set. So it's a what's the VR helmet. Okay, and in the VR helmet, there are two cameras capture the movement of the user's eyes, and when it moves, okay, it will generate this one. Most of them, the grayscale, it means there's nothing changed, and only when you move your eyes, there will be some changes. So again, they want to detect or estimate what is the new character location or guess of the eyes. So because this is a competition held in CPR 2024, so the big brand teams, the set, there are two members. They are Pi and Coin. So as you can see, they are ranked the third in the competition, and their performance is 90. So their P10, P5, and P3 are three different metrics. Their performance is 99. So just take a look of these numbers. Okay, so this is their experimental result on the same data set, but use their new algorithm. So this is their previous algorithm, and this is their new algorithm. Their performance increased and become the best among all the participated teams. Okay, the third dataset is the Prophecy. Okay, what is Prophecy? It is a company in Paris. Okay, it is the IC design house for the image sensor. And again, they create they generated the images are the event image rather than the RGB image. So what's the special? The special is they can their sensor can capture the world to generate a very large image. They are totally 1 megapixels. So in the rosin dataset, you can see most of them are rosin. You can see there's a road, building, and trees. There are two different boxes here. So this is pedestrian, and this is car. In the yellow box is a car, and in the green box is a pedestrian. So this is also pedestrian. Okay, so in this data set, okay, let's see the result. So first, the retina net, it is an existing data set proposed in 2018, I think it is 2019. Okay, it is the it was the state-of-the-art object detection algorithm in 1918, and but however they use the RGB image as input. So if they change the input image from RGB to gray, then they can create a gray retina net algorithm. Okay, so this is the performance, and they use 32.8 mega parameters. And the red is what? The red is, okay, so this is a paper. When the prophecy generation 4 rosin object detection dataset was released in 2020 in the NERPS IPS conference, they also released an algorithm. The algorithm is called RED. So there are two measures. First is mean average precision. The higher the better. It means you can, so it's because there are many classes in the image. The mean means average of each classes, and the average precision means how accurate your detection algorithm can recognize the location of those objects. So the higher the better, and the parameters is lower the better. Okay. So they compare the existing algorithm and the red algorithm proposed by the Perot, okay, and their new algorithm. So their new algorithm can generate the best mean of average precision, but they use much less parameters. So this is a very good improvement. Okay, so my conclusion is, okay, this paper is well written, and the improvement is quite promising. And I think the paper will be published somewhere in a high quality conference. So what I want to talk to you and including Xiaoming is, okay, you choose a very good paper. But however, as we can see, the algorithm works on event videos rather than RGB videos. So my next question for you is, are you going to use the event video to recognize your hand gesture? I don't know. Okay, it's up to you. If you want to do it, where can you get the event camera? I don't know. Okay, so because most of our cameras are RGB camera, and some of them we have the depth camera or infrared camera, but the event camera is quite rare. I personally even don't have one. Okay, so I hope you, with my explanation, you can get a concept what this paper want to do, and okay, what technique they used, right? Okay, then I'm talking about the MediaPipe head. Okay, so I googled it. I found two papers related to the MediaPipe. First is the paper published in CPR 19. It is the MediaPipe, a framework for perceiving and processing reality. Okay, in this paper, they talk about the whole architecture of MediaPipe, because you know MediaPipe includes several components: head, face detection, and whole body pose estimation, and facial landmark localization, etc. And I found another paper. The title is MediaPipe Heads, so it is highly related to our topic. let's see. Okay, and okay, so I think the important message from the first paper is MediaPipe runs on TensorFlow Lite. TensorFlow is the framework provided by Google. Okay, so MediaPipe is also the package provider, so it makes sense. They use their own framework. Okay, the important message from the second paper is MediaPipe head is an open source library, so everybody can read their source code. And let's take a look at what their source code, where their source code is. So once we click here, okay, you can go to the GitHub and see this is the MediaPipe head source code. But however, it's not easy to go into those source code. Okay, we can. What I want to do is just read their papers and understand the concept or components they use. Okay, so as you see this graph or this figure, it is presented in their paper, in the CPR Workshop 2020 paper. And here you can see, it means there is, let's go experience flow. When you have an image from the camera, first you will do a hand detection. In this paper, they mentioned it is a palm detection rather than a hand detection. So what's the difference from a palm and the hand? Fingers, right? Your hand will have 5 fingers, but your palm don't have the finger. So that's the difference. And in this figure, in this block, they mentioned it's a hand detection, but in their paper, they emphasize it is a palm detection, right? So when they detect the palm, they will crop the region containing the palm and do hand landmark localization. Right? And finally, they will draw the localized point out and show it on their display. Okay, and this is their latest graph. Okay, this is shown in their GitHub rather than from their paper, because you see their paper was published in 2020 and now it's 2024. There should be there might be some improvement during the 4 years. Okay, so let's take a look what difference. The first is they mentioned there is a tracking part. In their paper, they didn't mention any tracking component, but in their latest graph, there is a tracking component. And second, they correct the head detection to the palm detection. So there is a palm here. And for the remaining part, okay, because they didn't release a new paper, so and I didn't jump into their code, so it's difficult for me to understand what is the region of interest from landmark and the region of interest from palm detection, right? Okay, so what I'm talking about is their paper. Okay, so from their paper, they mentioned their palm detector is modified from their blade face. So let's take a look at what is the blade face. It's a face detection. So and I found that there is an online demo for the blade face. So let's take a look. Okay. So this is as you can see, and you can see the blade face here. However, there is no other option. We only can use this, right? And we will take a look of the blade face later when we compare it with the cascade of classifier. Let's take off, right? And let's go back. So okay, so this this is the part of the place face. And the place face is how do they create the place face algorithm? It is from SSD and MobileNet V1 and V2. Okay, so when you use MediaPipe head, you already use MobileNet V1 and V2 already. Okay. And okay, the second part is they include feature pyramid network and focal length to create their blast pump. Okay, so there are two different sources for the algorithm. Okay, first, so let me explain what is anchor box. Because SSD is an algorithm, and they modify the SSD by adding the anchor SIM, a GPU-friendly anchor SIM based. Okay, so let me explain what is anchor SIM and why do they need to do it? Because when they design the MediaPipe head, they expect that the algorithm is running on a mobile device. So when the computational resources is very, very strict on a mobile device. So they want to use as much as possible resources to speed up the algorithm, GPU. And the mobile devices have their own GPUs. So if they can, they want to use the GPUs on the mobile device. So they modify the SSD by using cell phone or mobile devices GPU. Okay, so what do they do? First, let me explain what is the anchor boxes. So the anchor boxes was proposed by the paper Faster RCNN. It was a NIPS 15 paper. Okay, so and the anchor boxes, the concept or the practice was very popular during 2015 to 2019. Okay, so the idea is, when they do convolution for a given image, they will create a feature map. And from the feature map, for every region, they will use the features in this window or this region to predict those some existing classes there. And how do they class? They first use some anchor boxes. It means predefine the shape of different aspect or different angle. So this is a small square, and this is a larger square, and this is the tall rectangle, and this is a flat rectangle. So those are those anchor boxes. When they slide the window to a certain position, they will use those predefined rectangle to generate the probability of certain classes. Okay. So this, when you take a look, so this is a person. A person usually is the tall, it fits the tall rectangle shape. And this is a bus. And the bus usually fit the square rectangle, a square or the flattened rectangle. So it means for certain classes, the probability of a certain aspect of the rectangle is relatively higher. Okay, so let's talk about the SSD. The SSD is an abbreviation of a single shot detector. So what does it mean, single shot? Single shot is, it doesn't use two networks to predict, to detect. What does it mean, two networks? So here, the Faster RCN was the state-of-the-art detection algorithm in 2015. It consists of two networks. First, it will create proposals. Proposals means, given an image, some regions may contain an object, and some region may not. Okay, so what is the proposal? It means when you see this region, it is very flat. There's no contrast at all. Or this region in the sky. So it will predict that there's no object there. And proposal means it predicts there might be something in a specific region. So this is first network. And when they generate many proposals, it will use a classifier to predict what is the highest probability of that proposal. So there are two steps for detection. And SSD remove the two steps. It only use a single proposal network. It's only a single network to generate the predicted bounding boxes and its probability. And the SSD algorithm is VGG16 based. It is similar to the YOLO V1. YOLO V1 was published in arXiv in 15 June, and it was become a CPR paper in the following year. But so you can see SSD CPR YOLO V1 was published first. Then SSD take a look of the YOLO, and if they want to claim they are better, they need to compare the state of the art at that year. That is YOLO V1. So okay, let's take. So this is the result generated by SSD, and let's take a look of their difference. So this is architecture of SSD. What does this mean? Okay, so and this is the figure from our textbook 3.630C. It means given an image, it will generate many different many feature layers of different scales, and in each scale they will predict some bounding boxes. So this is approach used by SSD, and SSD is the first algorithm using this approach. Before SSD, for example, like a faster RCNN or YOLO, they use this approach. It means given an image, when they apply the convolution neural network to generate a layer by layer, so usually the resolution of the layer will become smaller and smaller. It may caused by the maximum pooling or the stride. And when they generate a certain layer, they will use only a single layer to predict object in the image. So as you can see, from this layer, they generate some bounding boxes. And from this layer, they also generate some bounding boxes. So for each of them, they will also generate some bounding boxes. So in total, you can see the number. There are more than 8,000 bounding boxes per class. And for YOLO, it only generated 96 bounding boxes per class. So you can see, after they generate a lot of bounding boxes, they will apply the non-maximum suppression to remove most of them and only reserve the best, the highest probability one. So they will generate a result like this. Okay, so let me show this figure. So the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, S4. They are the series of YOLO. They are developed by different companies. The YOLO V1 and the V2 and V3, they were developed by the University of Washington. And the 4, 7, 8, 9, they are developed by Academia Sinica in Taiwan. And the 5 was developed by the Ultralytics. Okay, this here, the X and the 6, they are developed by MagV and Meituan. Both of them are Chinese companies. Okay, so here, SSD was published in ECCV or CPR? ECCV 16. Okay, so it's around here. Before YOLO V2, okay, it was published. Okay, so this is the, okay, I should say, today, is there there are very, very few, I should say, the concept of your SSD has been used by other detectors. So there's no following algorithm for SSD. But however, YOLO, they are still researchers. They are doing research for the YOLO. So the latest one, YOLO V9, was published in February this year. Okay. So for every different generation, there are some improvement, and make it better. So let's take a look of the YOLO V9. YOLO V9 is this one. When you use the same parameters, your AP is the same as the mean average precision. Some people call AP and some people call MAP, but the meaning is the same. Okay, when you use the same number of parameters, you can generate a better performance. So, and the improvements here, there, and okay. However, I didn't read every paper of those YOLO generation, so I don't know the detail. I only know they are keep improved. Right. So you can, let's take a compare here. For this one, this is the RT deter. It is the state of the art because it can generate the best performance, although it uses many parameters. And if you want a efficient and quick detection algorithm, then it is this. It is the YOLO NS. YOLO NS is here. Okay. When you restrict your number of parameters less than 10 mega, okay, the best choice will be YOLO NS. And the YOLO V9, okay, here, it has several models. When you use a small model, it is the best performance. When you use a large model, it also is a state of the art. So the contribution is quite significant. Okay, now we have a concept of what the SSD is, and the MediaPipe had used not only SSD but also mobile net. So let's talk about what mobile net is. It was first published in Archive 2017 April, and it is developed by Google because of Android. Android is a very important market for Google, so they need to develop some neither classification algorithm or detection algorithm so that they can sell they can keep the market share of the mobile operation system. Okay, so their purpose was to create a very, very lightweight network. So how do they do? Their innovations, they developed a depth-wise separable convolution. So what is it? The depth-wise separable convolution, it means a standard or a typical convolution can be separated into two steps. The first step is depth-wise convolution, and the second step is point-wise convolution. And what is point-wise convolution? It is just the one-by-one convolution. Okay, so let's take a look of what is standard convolution. Standard convolution means if you have a feature map and the size is the depth is df, the height is df, and there are n channels. So this is the size of your feature map. And the standard convolution, so this is the standard convolution kernel. There are also n channel, and the kernel usually is much smaller, so it is dk by dk. But you have n kernels, so the total is n. Okay, so the output size will be what? This convolution with this kernel, so your result will still be df times df. Suppose you have some paddings around the corner. Okay. And the new number of channels will be n because there are n channels. And the total computational load will be, it means how many multiplication and addition you use. It will be dk times dk times m times n times df times df, right? Okay. And when the mobile net, it proposes the combination of two steps. The first step is the depth-wise separable convolution. It means what? You have n channels, right? Now you don't convert when you have a convolution kernel, you only convolute it with a specific channel rather than every channel. So this is the separable, the depth-wise. Depth means the number of channels you used. Okay. And when, okay, so now your input feature map is the same, df times m. But every channel has their own kernel. Okay, it is size of dk times 1 because it's only convoluted with the channel rather than every channel. Okay, so you totally have m channel. So the convolutional load will be dk times n. There is no m here because it is separable. Okay. So this is the first step. And the second step will be you have many 1 by 1 convolution channel. A totally number is m. So for each one, you will convolute with the result of the first step. So so this is the intermediate feature map. It means the result of the first step. It is df times m. Okay. And use the 1 by 1 convolution channel. The computational load for this step will be df times m times n. Okay, so let's calculate how many computational load we can save. Okay, the cost for the computation load for the standard convolution is this one. And the depth-wise separable convolution will be this one. So this is the first step plus the second step. Okay, and their ratio will be this plus this divided by this to become 1 over n plus 1 over d squared. Okay, so if your convolution size is around 3 by 3 and your number of channel is 250, the ratio is only 1/9. So you can significantly reduce the computational load. Right, so let's take a break. So from here, you can see the mobile net can significantly reduce the number of parameters, or the number of the computational load. So this is the mobile net layer. So okay, the left part is the standard convolution layer. It is a convolution, then do Bayesian normalization, and then there's a activation function. And this is the architecture proposed by MobileNet. It replaces the standard convolutional layer by first use a 3 by 3 depth convolutional layer, and after that there's a Bayesian normalization loop, and then this is the point-wise convolution. Is 1 by 1, and the Bayesian normalization and the loop. Okay, so let's compare with the number of parameters they used. For the set SSD 300, so SSD is here, what we mentioned. This is SSD. And what is the 300 means? Suppose the input image, the resolution is 300 by 300. You can see this is 300 number here. Okay, so there are several different models, 300 by 300 or 521 by 521, etc. Okay. In this case of SSD 300, okay, the SSD 300 was originally developed using VGG. So how many parameters do they use? They use 33 million. And the SAT300 can also be implemented on the Inception Net V2, that is the Google Net, because as we can say, Google Net and the VGG Net was published in the same year, 2014. And the VGG Net is a huge net, and the Google Net is much relatively small. So Google Net still need to use 13 million parameters. If they replace the 3x3 standard convolution layers by their depth-wise separable convolution, then the number of parameters will be reduced to only 7 million, so that the network can run on mobile devices. And the computational load measured in billion of multiplication and addition. Okay, it also significantly reduced from 35 billion to 1.2 billion. So that it, for mobile devices, the CPU and the GPU is not powerful as the desktop. They also can run the mobile net classification, or they can use mobile net to execute some classification detection task. But however, there is a trade-off. The trade-off is the precision, performance. So which is the best? Okay, it is the Inception V2. And if you replace the convolutional layers with the depth-wise separable convolution, the performance will slightly reduce to 19.3%. However, this is a trade-off. If you want your model light and run fast, you need to sacrifice some accuracy. So okay, they implemented the mobile net on the image network. So you can see the output scores. There are totally 1,000 classes in the image net. So they implemented the algorithm, actually the architecture to develop this mobile net network, and let's see their accuracy performance. So this is the 1.0 mobile net 224. The 224 is the input resolution, 224 by 224 for ImageNet, because the first network algorithm, the AlexNet, used this resolution. So the following researchers, most of them will follow the same resolution for a fair comparison. Okay, so for VG16 and Google Net, they all use the same resolution as the input. So you will see the 224 here. And the 1.0 means, okay, let's see here. There are M channels for the input layer. And the output channels, number of output channels is M. It is adjustable. You can reduce the number of M and N to reduce your network architecture. So here is, they introduced the parameter 1.0. It means if you use the full number of channels, then use 1.0. Otherwise, you can choose other parameters, for example, 0.75 or 0.5 or 0.25. It will further squeeze the network size. But however, the performance will also be reduced. So let's see the comparison again. If they use mobile net, then the number of parameters is only 4 million, compared with Google Net and VGNet is relatively smaller. And the number of multiplication and addition, they only use 600 million, compared with the 1.5K and the 15K is much smaller. And however, about their performance is even slightly better than Google Net. but worse than the VG16. So that's the value of the mobile net. It significantly reduces the number of parameters and computational load, but only sacrifice a piece of the performance. Okay, that is the mobile net V1. And what is the mobile net V2? Well, the mobile net V2 was published a few months after the mobile net V1. It adds the residue to mobile net V1. So it means, just like the ResNet, they learn the residue. So from the input layer to the output layer, there is a shortcut. And their network learn the change of the residue. And how do they learn the change of residue? Following the same approach. The first, there's the depth-wise convolution. And the second, there's a one-by-one convolution to generate a channel of the output layers. And they even introduce an interesting activation function. It's called ReLU6. So what is ReLU6? It means, as you can remember, ReLU means for the negative part, the output value is 0. For the positive part, the output value is the input value. And the ReLU6 means if your activation value is greater than 6, you only output 6. Okay. But however, I didn't see many following papers use the ReLU6. But when you see the term ReLU6, you can understand what it means. Okay, all right, and this is a comparison of mobile net V1 and V2. So this is SSD 300, SSD 512. This is the difference on the input resolution. And this is YOLO V2. Okay, so let's take a look. YOLO V2 was here. It was published at the end of 2016. And then YOLO MobileNet V2 was published in 2018 January. So that they can compare with their performance against the YOLO V2. And so this is the SSD Lite. SSD Lite just the SSD and replaced the standard convolutional layer by the depth-wise separable convolution. And this is their new version. This is use the residue. Okay, so it can further reduce the number of parameters from 4.1 million to 4.3 million, and reduce the computational load from 1.3 billion multiplication and add to 0.8 billion. As a result, if they run the algorithms on a mobile phone, then it only takes 200 million seconds to process the image. Compared with their previous version, it takes 270 million seconds to process the image. So you can see there is an improvement around 20 to 30%. Okay, so here, let's take a look of here. We talks about the first. Okay, so SSD is a detection algorithm. MobileNet is a method to reduce the computational load, and MobileNet V2 it further reduces the computational load. Combine the three components, we will get the blaze phase. Okay. So let's go to the blaze phase. Okay, so the blaze phase was published in CPR workshop 2019, and it is similar to mobile Net V2 plus SSD Lite, but they are slightly different. The first difference is SSD Lite, it only uses 3x3 convolution, and the blade phase uses the 5x5 convolutional kernel. And the reason is they found many cell phones have a very powerful GPU. I should say not powerful, very efficient GPU. The GPU can do some parallel processing so that if they enlarge the convolutional kernel, the processing time for 3x3 and for 5x5 are similar. If they are similar, then why don't they use 5x5? Because if you enlarge the convolutional kernel, you will enlarge the perception S ratio. Okay. And the second difference, they create a new architecture called double blaze block. It's duplex. So this is the single blaze block, okay, and this is a depth-wise convolution and the one by one. And the path, maximum pooling and the channel path, that is the architecture proposed, residue architecture proposed by MobileNet V2. And their double blaze means after the first depth-wise and one-by-one convolution, they add an extra depth-wise convolution and one-by-one convolution. So this is called a double blaze block. Okay. So this is the architecture for their blaze phase. Given some input feature layers, they use their blaze block to generate the fuel. And at the end of the architecture, they generate the bounding boxes to predict where those phases are. So this is like an SSD. Okay, so this is their performance comparison. If they just use MobileNet V2 plus SSD, then okay, their accuracy is 97.95, and the inference time in terms of millisecond on the iPhone XS, okay, it takes 2.1 millisecond. But if they use their blaze phase architecture, they not only improve the average precision, but also reduce the inference time. So that's the reason why they modify the MobileNet plus SSD. And they not only compare on this single model, iPhone X10, they also compare their algorithm against MobileNet V2 plus SSD on iPhone 7, Google Pixel 3, Huawei P20, and Samsung Galaxy S9 Plus. Okay, on those models, they all produce run more quickly to generate their result. Okay, there's a question. What is their data set? When they report these numbers, okay, so they mentioned they use a private face image dataset containing 66,000 face images, and their test data is 2K private face images. Both of them are private. Okay, we have no way to reproduce their result. We only can either trust their method or just use their algorithm. Okay, now we see what the blaze phase is. When you replace the phase algorithm with face images with palm images, you get the blaze palms. So that's all. Okay. Just replace the training set. The algorithm is the same, right? Okay. Okay. Now we are talking about another branch. Okay, let's take it back to the graph here. Okay. So the another branches, now we have the blessed phase. You can, okay. The blessed phase was published in CPR 2019, and there are another branch of detection. It is called the feature pyramid network and the focal length. It was published in CPR 17 and SEC 17. The blessed phase include the blessed pan includes the blessed phase, but also the two new components. So let's take a look at what the pyramid feature pyramid network is. Okay, so the concept of the feature pyramid is like what? They consider some existing approaches for detection. First is this. Given an input image, they will create an image pyramid. So in the pyramid, each layer is slightly smaller than previous layer. Then from each, this is image, they apply their detection algorithm to detect the location and their class probability on each image. So they will predict it several times. Okay, it is very straightforward approach, and we will see it in next or this class when we talk about the classified cascaded classifier. We will see this approach, but the problem is the drawback of this approach is it's very expensive. You need to generate several images and apply your algorithm several times. So the second approach, it is used by RCNN and the later fastest RCNN and the latest faster RCNN. The idea, or even in the YOLO, the idea is given an image, they will use convolutional layers to generate a destination feature map and use this feature map to predict the location of those classes or objects. Okay. So, okay, that is the state of the art during 2014 or 2015. Okay. So SSD used this approach. Given an input image, it will generate many feature layers, and from each feature layer, the feature layer will be used to predict the object of those classes. But this is a good approach, as we can see SSD generates better performance than YOLO. But in this paper, CPR 17, they argue that there is a difficulty because the meaning of each layer is slightly different. As you can see, in neural network, the early layer, they will detect, for example, age, and in the middle, they will detect some patterns like a texture. In the lattice layer, they will detect some patterns like the shape of certain animal or etc. Okay, so for different layers, you need to develop the different. Okay, actually, they are inconsistent. Therefore, if you want to use those consistent layers to predict the object, you may not generate the best performance. So in this paper, they propose create a pyramid of features. It means given an input image, they will generate the pyramid of the feature layers and use those feature layers to generate another consistent feature pyramid and use the pyramid to predict objects at different scales. So this is the concept of the feature pyramid network. Okay, and the same thing of the picture pyramid network, they in the same year. So you can see this is CPR 17 and this is ICCV 17. So CPR take place in June every year, and ICCV take place in October. So the same thing, they introduced a concept of focal loss. It means some objects or some classes are easy, or some examples are easy to classify. So, and some classes are difficult to classify. For the easy or well classified examples, they reduce their weight. And for the difficult ones, they increase their weight so that they train a network. Because since easy examples are always, I should say, the probability is always high. If their probability is so high, it's very difficult to make mistakes. Therefore, they will have little impact of the overall loss. So let's see what is the meaning of those different curves. So they introduce a parameter gamma. The gamma, when you adjust the gamma, you will adjust the distribution of those loss. When your gamma is 0, it means this curve, okay, the yellow one. And when your gamma is greater, so say 5, then your curve will be this. Okay, what does it mean? Say if you have a example, it will generate only 0% probability for certain classes. And then if you set the gamma as 5, then the ratio of this and, for example, this point, it will be significantly enlarged compared with the case of gamma as 0. Say, let's take a look. If you have a example, and when you set the gamma as 0, and the loss here may be 0.2, and here maybe 1.0, so the ratio is 5. And when you set the gamma as 5, the ratio here, say, it may be 0.02, but here it is maybe 0.14. Then the ratio will be 7. It means you pay more attention on the difficult examples. Okay. So when I apply the focal loss, when I just adjust the gamma to pay more attention to the difficult examples, let's take a look of their result. So this is their, okay, so let's see. Say, let's take a look of the B. B is SSD 321. That is what? That is our smallest, quickest network. Okay, so you can see the inference time is the shortest, and however, its average precision on the COCO dataset is around only 28. Okay. And you can see C means the SSD, DSSD 321, and so D is the RFCN. It means the faster RCN but replace the CN by the FCN. Okay, and this is SSD. E is the SSD 513. Okay, and the G is the another algorithm. Okay, when they apply the focal length on the same test dataset, they generate the result for the proper one. It means they use the Rentana. Okay, okay, they use the ResNet 15 as their backbone. and they adjust. When they apply, okay, let me explain. Here, this is a pyramid, feature pyramid network. They use, so they have several choices. They can use ResNet 15 or ResNet 101 as the backbone. Okay, when they apply the ResNet 101 or ResNet 15 as the backbone and apply the feature pyramid network, okay, they will generate a certain result. And when they apply the focal loss, they call the network retina net. So therefore, they generate two curves of the retina net. So this is the ResNet 101. It means it is because the network is larger, so it takes more time to inference, but its performance is also better. And the RetinaNet 15, it is a smaller network. It runs faster, but the performance is relatively lower. Okay. However, compared with those existing methods, only adjust the distribution of the difficult and easy examples. They generate the best result because they can recognize difficult examples more accurately. So, all right, now we converge AV component into the Blaze pump algorithm. So this is the architecture of the Blaze pump. For this part, it is a Blaze face. Okay. And for this part, it is the image pyramid. In the Blaze face, there is no image pyramid part. And in the Blaze pump, they added it. Okay. So let's see, there is a comparison. Or we say it's an ablation study. It means, so this is the decoder, it means the image pyramid part. If they have no image pyramid and they only use the cross entropy loss, it means there is no focal loss. Then their average performance is 86%. If they add the feature pyramid, this part, okay, they improve their performance to 96%. And if they introduce focal loss, then they further improve their performance by 1%. Okay, so this is the result. All right, so let's take a look of the Blaze pump. Okay, because MediaPipe also provides an online demo. So let's take a look. Okay, so you are familiar with this. This is a MediaPipe, and according to the paper, first they need to detect the pump. Okay, so what will happen if I use a glove and okay, it doesn't detect my hand because it doesn't detect my palm. This is not a common color for the palm. Okay, okay. You can see, right? But however, the paper was published in 2020. Now it's 2024. There might be some adjustments. So let's try to adjust. Let's take the parameter. So this is a hand detection confidence. I guess it is a confidence for detection of palm. Okay, and the second is hand presence confidence. So we will talk about what it is. Okay, and the third is the tracking confidence. This part is not mentioned in their paper. So okay, I think it is a new component added after the paper was published. All right. Okay. Okay, now let's talk about their training set. According to their paper, they have three different types of images. First, the real-world images. Okay, these are real-world images taken in the wild, 6K, and taken in their office, 30K, 10K by 30 people. And there are also 1000K synthesized images. So these are synthesized. They just used a commercial 3D product to synthesize those hand and some synthesized background. Okay, so there are total 116K images to train their model. It's the number is quite promising. Okay. And how do they detect the palm? They only use the 6K hand images in the wild. Okay, that's the part of palm detection. And now there's another component. It's the finger or hand localization. How do they do it? They also mentioned it in their paper. So they mentioned they use the same method as the Simon et al. Published in CPR 17. So that is the okay. So this for these two components, they use to localize the 21 key points, and then they also need to detect the hand presence. It means what is your orientation of your hands, and then they also want to detect is this the left hand or the right hand. So this is the handiness. Okay. They merge often into a single network. So let's take a look. What is the Simon et al.'s method in CPR 17? Okay, so the paper is hand key point detection in single image using multi-view bootstrapping. So what is? Let me explain this idea. Suppose you have many cameras, and those cameras all take a picture of your hand. Therefore, some view will be very easy. The images from some views will be very easy to localize your key points on your hand, like the first one or the second one. Okay. Once they can recognize the key point of your hand, they can create a 3D structure. Use the 3D structure, they can treat it as the ground truth and to train it detectors from the difficult viewpoints. So, for example, this is the failed detection. Okay, once they have the 3D models, they can use this to improve what it means reprojections, the correct key points onto the hand. So they will create the result like this, and then use this result to train the detectors for the viewpoint. So this is their concept. So So when I read the paper, I am very curious. What is their hardware devices to capture a hand from different viewpoints? Okay, so they mentioned how they do it in another paper. It is the ICC paper. Okay, it is the Panoptic Studio. All right, so it looks like this. It's quite a huge room. And this is a conference paper, and they want to submit a journal paper. So they wrote an archive paper in 2016 December. But however, I didn't find the journal paper accepted by any journal. Okay, so there is only archive paper. Okay, never mind. Let's take a look. They create a very huge studio. And in the studio, there are projectors. So this is a projector. So you can see here, this is a projector. There are many projectors. And there are low resolution cameras in the red circles. So this is the resolution is only VGA. There are totally 480 cameras. Okay, so, and the sign here, this is also a sign. This is Kinect depth cameras. So there are also many depth cameras. Okay, so let's take a look of their demo video. Okay. So the DMC means distributed module control. Okay, so this is quite a huge device. Okay, the small hole is a VGA camera. Okay, so this is videos taken by a single VGA camera. Okay, there's a totally 480 input videos. And then once they have those data, okay, they can use those data to reconstruct their 3D models. So you can, from this region, you can see the different body components. So this is an illustration for another sequence. Okay, so it's the end of the demo video. Okay, you can see the excellent hardware devices. They can create a very, very interesting data so that they can do research on those data. So which university is it? Carnegie Mellon University. Okay. One of the top 4 computer science universities in the world. Very, very. So how much money do they need to use to build such a studio? I don't know. So I only can say, oh, very excellent. Okay. Okay, so the Senti. So you see the way he and those authors are from the Carnegie Mellon University, the Senti. Okay. So why we need to mention it? Because here, this is the idea. How do you improve your hand key point detection from different aspects? Why do we need to care about it? Because when we put our hand in front of our camera, okay, might be the easy viewpoint. It might be very difficult viewpoint. They need to have multiple detectors for different viewpoints so that they can correctly recognize your key point, even it is partially excluded. But however, this is just idea how to train classifier from different viewpoints. But what is the architecture to train a single classifier? So they mentioned they use this the convolutional pose machine. It is a pose estimation algorithm. So let me explain how does it do. Sorry. Okay, basically, given an image, they can extract some features, and from the feature, they predict the probability of key point. Okay, so how many key points they want to predict? There will be a p+1 layers of the output, and once they have the first result of the first stage, they will use the same input image and extract some feature and concatenate the image layers with the new feature maps, and then generate the result of the second stage. And then the third, fourth, fifth, and sixth stages are the same as the stage 2. Okay, so it run the process iteratively for 6 stages. They will generate a probability map for AV key points. And the post machine, in fact, it was existing paper published in ECCV 16. And the convolutional post machine means they use convolutional neural networks to extract the features, to replace the man-made features. Okay. So here you can see this is a 9x9 convolutional kernel and 9x9, 9x9, 9x9. So features are extracted by those kernels. So this is the stage 1. And when there is some pooling layers, with those pooling layers, the perceptive field will slightly increase, and become larger and larger. For some key points, they require large perceptive field to generate a better result. And why it is P+1? Because there is a class is background. It is unrelated to your key points. So this is a concept. And let's see some results of the algorithm. So as you can see, there are 6 different curves. Stage 1, the result is this. Stage 2, stage 3, stage 4, and it is according to their experiment. If you use 6 stages, the performance is almost saturated. Okay? So you don't need, and if you use more stages, you need to learn. You need to, your network will become larger. There will be more convolutional kernels and more parameters. Okay, so they are trade-off, and they finally choose the number of 6. And this is the they tested their algorithm on 3 data sets. This is one of them. This is the LPS data set. LPS means these sports posts. These should be a name of the university. Okay. And they also, this process, it means PC. PC means person-centric. In the original image, the person is not at the centric. So they slightly crop the region of the person, okay, so that they can apply their algorithm to detect the pose, estimate the pose more easily. Okay. All right. So, okay. Then, now we have the algorithm. And when we apply to our hand, it will look like this one. The MediaPipe used a model of 21 hand landmark key points. And as you can see, there's very similar figures shown on your own slide. And this is their locations. So this is 1, 2, 3, 4. It will generate 22 probability maps. And so if you use this heat map bar, then you will see for this key point, it is brighter than others. And some are easy to recognize. For this one, okay, so you can see its color is close to red, and it means the probability is close to 1. And for some of them, for example, this one, it is slightly difficult to localize. So the probability is around 0.4 to 0.5. Okay. So however, apply this algorithm and the previous one, this one. So you can train several detectors for different aspects and always generate acceptable performance to localize your hand landmarks. Okay, so now this is the introduction to the MediaPipe hand, because I think at least half or 1/3 of you use the MediaPipe hand to do your homework too, right? Okay, so now you now have a concept of how it works. Okay, and then you can see it uses at least 6 or how many? 1, 2, 4, 1, 2, 3, 4, 5, 6, 7, 8. 8 state-of-the-art papers of those years. Okay. So MediaPipe head very easy to use, and now you have the concept how it comes. So it is useful. I should say, you now get the experience when you use something easily. Behind the package, okay, there are some interesting or intriguing knowledges there. Okay, so this is SSD, is a detection algorithm, and plus MobileNet V1 and V2, it become SSD Lite. Okay, and the SSD Lite is used to become the blade phase. It is just slightly reduced the convolutional size 3x5, 3 to 5x5, because it found that some mobile GPUs can be used to process the 5x5 convolution. And also they developed the double blade block, okay, to prove this performance. And then the feature pyramid network and the focal length, they are two improvements. So the feature pyramid, it created a consistent feature layers to predict the object, and the focal length improved the detection of difficult examples. And finally, the multi-view bootstrapping, they can help us to recognize hand landmark from different viewpoints, and they use the convolutional pulse machine as their backbone, and so it merges to the palm detection and the landmark localization and become our MediaPipe hand. Okay, here there's no, it doesn't mention the tracking component, so we don't know how it handles with the tracking. But however, at least we know how it handles palm detection and finger localization, right? Okay. Okay, so in this course, I want to talk about the Cascaded Classifiers. Why? Because in your homework 1, I found at least 3 or 4 students, they used this piece of code. So what is it? This is the OpenCV's Cascaded Classifier. Okay, so for example, this is the homework code from Wei-Lun, and this is the code from Kench. They all use Cascaded Classifier. Okay, yeah. But however, what is it? I want to explain it now. It's very easy to use. Okay, and what can it achieve? Is okay. Let's see. Let's take a look over here. Okay, I just copy a piece of code from somewhere in the internet, and if I run it, okay, then I will generate the results. Now, okay, it detects my face and my eyes. Okay, that's all. And right. Okay, so let's prepare. So if you go to OpenCV's website, basically the information is provided on their website. Okay, the big concept is, so you can see this figure. So this is the feature they extract from the image, right? And however, if you want to go deeper, you can read the paper of Viola and Jones. They published this method and call it rapid object detection using a boosted cascade of simple features. It was published in CFR 01 23 years ago. Okay. And there is also a journal paper published in 2004. Okay, they are mostly the same but slightly different. And my topic in this course are mostly extracted from their journal paper because it covers more details. So first, what is cascade of classifiers? Okay, it means, so this is the cascade. This is a fall, and there are several stages. The fall flows from the top to the bottom through each 1, 2, 3, 4 stage. So that is the cascade. And the cascade of classifiers means you have a first classifier, and the classifier will generate some false example. It means there is no face in the region, and you will use a second classifier. Okay. And the second classifier will also go through the image, and they will generate a lot of false regions. It means there's no face in it or any object, because face is just an example of the object. And there go third classifier, and there are a lot of classifiers. But however, each classifier has different property. For the first classifier, it's just roughly go and run very, very quickly, go through the image. They will generate a lot of false positive. It means it is not a face, but it is saying, okay, it might be a face. Okay. And why need to such a design? The first classifier is very cheap and fast, but it will generate a very high false positive rate. Okay, but it can roughly reject many obvious non-face image. And okay, the second will be slightly expensive, but the accuracy is slightly higher. And the later the classifier, the better the performance, but also the more expensive of the computational load. Okay, why do they need to design such a cascade? Because they want to because on an image, most regions, okay, so there are only very few regions have a face. For most other non-face regions, they want the combination of those classifiers can quickly reject those non-face regions and improve the overall frame per second. Okay, so so they show an image to show the ideas is feasible. So then let's take a look of the two curves. So this is a solid line and there's a dashed line. So let's take a look at the legend. The solid line means this is a cascade of 10, 20 feature classes. So, and the dashed line means it is a single classifier use 200 features. So you can see roughly the number of features they use are the same. Both of them are 200. But which is faster? Okay. And their RC curves are similar. Although this dashed line is slightly better. But however, what is their cost? The inference time is 10 times greater of the single 200 feature classifier over the cascade of the 220 features classifier. So if they want the algorithm can run very, very fast, they would prefer the cascade of classifier. Okay, so since there are many classifiers, so let's say how a single classifier works. Say they use the Haar-like feature. So who is Haar? Haar is a mathematical Alfred Haar. Okay, he proposed the Haar sequence in 1909. So this is the Haar sequence. You can see from the horizontal horizontal axis, this is 0.1.0, and then there's a negative 1.0. So it looks like this. So what it is? In 100 years ago, there is no concept of a wavelet. But when wavelet was developed, they found, okay, the sequence, in fact, it is the simplest format of wavelet. So it is called Haar wavelet. Okay, so right, it is a combination of a positive positive one and the negative one. Okay, so in the Viola and the Jones feature, they use the Haar-like feature. It means given a region, okay, they want to calculate the Haar sequence. So for example, for this region, there are many intensity, and then they will calculate the summation of this white intensity minus the summation of the pixel intensity of this region. So it's just like this one. This is the summation of the intensity minus the summation of this region of intensity. So this is the pure Haar feature. And this is another pure Haar feature. But however, this is not. This is just Haar-like. Because Haar sequence only contains a positive and a negative 1.0 region. But there are three regions. Positive 1, negative 1, and positive 1. And even for this D type, there are two positive regions and two negative regions. Okay, so they only say they use Haar-like feature rather than use the pure Haar feature. Okay, and as you can see, in addition to the 4 Haar-like feature, you can create a more Haar-like feature. Any combination of the black and the white regions. And however, in their paper, they restrict their algorithm only use the 4 types of Haar-like features, because if you add more Haar-like features, your model will become more difficult to calculate. Okay, now the next, the concept is, okay, sure, given an image, given any Haar-like feature, we can calculate it. And they also proposed a method called integral image to calculate those Haar-like feature efficiently. So the reason is, okay, if you have a very small image and there are only 24 by 24 pixels, then how many Haar-like features would you have? Suppose you only have these 4 types of Haar-like feature. Okay, the number is there are 160K Haar-like features. This means a lot. Okay, if you want to calculate a large number of Haar features, this takes a lot of time. So they propose the integer image. It means given any coordinate xy, they can compute the region of the integer, okay, the summation of the intensity of this integer at first. Then they can calculate those Haar features very quickly. The reason is, okay, first, the integer image is very easy to calculate. If they have this image x and y minus 1 already, then they can easily calculate x and y by these two equations. So it just means if you have a single pass, you can calculate the integer values for the whole image. And then, okay, if you want to calculate the region of D, easily you take the number of 4 integer value minus plus number of 1 and plus number of 2. 2 means what? For this region. Okay, this is a 2. And 3 means what? For this region, this is 3. So if you want to know the number, the region of D, then you can just use 4 plus 1 minus 2 plus 3 to get the value of this region. Okay, so here you can if you want to calculate the half aggregation, so how many points do you need to take? 1, 2, 3, 4, 5, 6. You just need to take the 6th point. You can calculate the half feature of the type A. Okay. So you don't need to sum every pixel up because it takes time. Alright, okay, now suppose you have 160K features, so which are good and which are poor, which is useful to recognize those face image which are not. So first, they need to compile a face image data set. So they do it by collecting face images anywhere. So they totally collect 4,900 and 1,600. All of them are very small, only 24 by 24 in grayscale. And they also compile a non-face dataset. There are 9,500 images, and then also the same 24 by 24. And then they manually check there is no face in the dataset. And here is an example of their dataset. You can see those images are not well aligned. There are many different pose, orientation, and brightness, age, gender, and races. Okay, it's a almost very various dataset. All right. Okay. Then, so they use the ADA boost algorithm to select which features are good and which features are useless. So the ADA boost, the full name of the ADA boost is adaptive boosting. It was proposed 6 years ago before the Viola and Jones algorithm. Okay, and it is an iterative algorithm. It means now you have around 4,900 images, and each image has a weight. You can adjust the weight. Initially, they are totally set even. And if the image is easy correct, then you can reduce its weight. Otherwise, you can increase its weight. Okay. And in addition to the 4,900 images, you also have 160K features. So this is a combination. How you need to adjust the weight of those faces and also the weight of those features, right? Okay. And then finally, you will figure out what images are difficult to classify and what features are useful to classify those images. So this is the algorithms reported on their paper. So let's take a look. So initially, this is the X, Y, and the X means image. And the Y means it is a face image or non-face image. Okay, so if it's a face image, it is 1. Otherwise, it is 0. So we initialize the weight. So the M means the number of face image. The L means the number of non-face image. So in the beginning, for face image and non-face image, we assign the same weight for that. But however, because the two data sets are the number of images for face and non-face are different, so we assign 1 over 2M and 1 over 2L for either data set. Okay, so as you can see, the weight, the sum of the weight will become 1. Then there is an iteration. Iteration means we will decide which is the best classifier in those T loops. So then we have totally 160,000 image classifier. It means we will have so many T's. So in the beginning, we normalize those weights. And then here we will find which classifier will generate the minimum error. Okay, so it means if they generate the best classifier result, we take it out and use the remaining features and do the loop again, and we find the second most effective feature. So this is if we have a hard-like feature, we will create a single weak classifier. So like this one. It means, so this is the input image, X is the input image, and F is the feature, a hard-like feature. The P and the theta are two parameters we need to adjust. Theta is the threshold. It means if the hard-like feature is greater than a threshold, we may use it to judge whether the input image is a face or not. And the P means we can use the threshold to set, do you want your threshold is a minimum or is a maximum? So P can be +1 or -1. If it is a +1, it means your if your hard-like feature generate a certain number less than the threshold, then I will predict this is phase. Otherwise, it will be the reverse case. Okay. So as this is an example. Given this image, and if you use this hard-like feature, is it effective? Can you use the value from this hard-like feature to predict whether it is a phase or not? Of course, you can try, because we have totally around one. So how many images do we have in total? We have around 1.5K. No, okay, 15K. 15K. Yeah, we have totally 15K images to test. You can use it to try each weak classifier. It means you can try each hard-like feature. Okay, so among those 116K features, you always find the best one. You can try this, try this, try this, try this. Just let the computers run. Okay? You also can find the effective feature. So, okay, this is their report. They tell us which two features are the best features. The first one is this one. It means if you see a black region almost cover your eyes, and see a bright region on your cheek, this is the most effective feature or most effective weak classifier to classify whether this is a face image or not. And the second most effective hard-like feature is this one. It means if you see a black region at the center and the two dark regions at its two sides, then it is very likely it is a face image. That's a reason why. Because human faces is a highly structured object. Everybody has two eyes. And at the region, you always have a dark region because the region of your eye is almost darker than your forearm and your cheek. And also, it is your bridge of nose is also brighter than your two eyes. Okay, so this is most two effective hard-like feature or weak classifier. So let's take a look. If you use the same hard-like classifier, but place them at different locations like this, will they generate a good results or good classification performance? No, they won't. Okay, because for this location, it is very difficult telling you whether it is a face or not. Okay, then now we know how to select a good classifier. We also have the concept of cascade of classifier. The next question is how to build, because you have several classifiers, how to build those classifiers. Okay, so there are some criterions. So they need to care about what is the false positive rate per layer. Layer means the classifier. And what is their overall detection rate they want. And what is the overall positive negative rate. So, okay, they use the three criteria to design their cascade of classifier. Okay, the concept is, in the first stage, they control. Okay, suppose I want the positive rate here is say 60%. That's fine. Okay, then on the second stage, they may want to increase to 65 and then 60, 70, etc. So that they can control the false positive rate per layer. Okay, so let's take a look of their test set. Their test set is the NIT plus CNU frontal face data set. This is okay. There are only 170 images, and there are totally 507 faces. Okay, so this but however, this is a real world data set. They are various size, light condition, races, and face orientation. This is not they are not the first algorithm to detect faces. There are many existing algorithms already. So once if you see this image, you can find it in our textbook. Our text mentioned that this image has been used by many existing methods. However, okay, so you will see the later. All right, let's take a look at it. So from this image, you can let me enlarge it. Okay, this face and this face are missed. They didn't detect it. And this is a false positive. This is a sucker, but it is recognized as a face. And here, okay, so this face, it is not detected, right? And also this face is also missing. So, okay, this, right? Okay, then, okay, so this is the algorithm, how they control each classifier, right? So we this is one of our criteria for startive rate. And this is another criterion, detected rate. Okay, so this is their algorithm. They how to control the positive rate and the detected rate. So they set some threshold. And how do they control it? Okay, if in the beginning they only use the positive images or face images, and if they add more negative images, they will reduce their false positive rate. So they will add more false non-face images until the criteria is matched. Okay, then they will go to the next layer or next weak classifier. Okay, so let's take a look at what is the computational load for their algorithm. Okay, they train their algorithm for several weeks on a single Alpha Station XP900 machine if there are 68 classifiers in the cascade, right? And because this research was done in 2001, and the 460 mega, it is the, I should say, a mainstream of those years. However, the two researchers, Chih-Yuan and Jones, they were researchers at the MER. MER is the Mitsubishi Electrical Research Laboratory, okay? And another is the researcher at the Compact. And this Alpha Station was a product of Compact that year. So they can access or borrow many machines, at least 7, to train the model in parallel, so that they actually train the model for 24 hours to find the best weak classifier and the cascade of those weak classifiers. Okay, so this is their design. Their design is this is the layer index, means the index of those weak classifiers. So the first weak classifier, there is only a single feature, and the second classifier has 10 features, and the third has 25. So the larger the index, the more the number of the feature they used, and they will improve the accuracy, but it is also more computational expensive. So okay, so all right. Okay, so how many layers do they? Okay, so sorry, this is a typo. This is feature. So in total, although not a feature. So layer means weak classifier. In total, they have 38 weak classifier and 6,060 features in their classifier. Okay. And let's see their okay, here I want to mention. In the beginning, we mentioned they only have 4,916 positive face images. And they do the data augmentation. Because for human faces, if you flip layer or vertically, this is still a human face image. So in total, they have 9,832 face images. Okay. So this is their approach. Given the image, how do they detect the faces from the image? Okay, here they use image pyramid. It means given an input image, it will slightly reduce the resolution from its original resolution to slightly smaller. So that is the case as mentioned in our textbook. It is a image pyramid, and for each layer of the pyramid, they will apply their cascade of classifier to detect whether there is a face or not. So they choose the parameter. The downscale factor is 100.5, and the step size means they need to scan every pixel. But they choose 1.5. It means for every 3 pixels, it only scans it twice. It matters because if you slightly change the parameters, you may need reduce the overall computational load, right? So, given an example, if they want to test the input image of the resolution 384 by 288 on a Pentium 3 machine, why it is patent 3? Because the paper was published in 2001, and the patent 3 is the available high-speed CPU of that year. Okay, it takes 0.67 milliseconds. Okay, let's see the comparison for two different settings. The first settings, if the first step, they use 1.0, it means for every pixel, they need to test whether it's a face or not. And the second setting is only the step is 1.5. It means for 3 pixels, they only check it twice. And the first scale means, given an image, do you want to scan the pixel? Scan the first, it means this layer. Do you want to scan this layer? Or do you want to scan from this layer? If you want to scan the original resolution, you need to scan more windows. If you just scan the first resolution, the second layer resolution, you can reduce the number of scanned windows. So this is the second configuration. So they compare how many windows do they need to scan from between the two configurations. For the first one, there are 75 million windows they need to scan. And then for the second one, there are only 19 million. So, and how about their performance? So let's see the difference of the two ROC curves. They are very, very similar to each other. For the first configuration, this is a solid line. It's slightly better than the second one. But however, the second one is much, much faster than the first one. So, okay, let's see their performance. So they, under the criteria of certain first part, okay, so I said there are several different configurations. So this is a 10 weak classifier, 31, 51, 50, and 60. The larger the number, it means the larger the model. Okay? And they can generate, if they have 78 detectors, their performance around 92.1. Okay, compared with some existing method, their performance is not the best. However, their speed is much, much faster compared with this Rolais paper. Okay, so this is Rolais method. Their performance is better, but it's better, and their speed is 15 times faster. Let's compare with this another paper, this one. Their performance is worse, but their speed is 600 times faster than the existing method. So that is the value of the paper. It can be executed very, very quickly. So let's recall, what is the title of this paper? It means it claims it is a real-time okay. It is a rapid or real-time, robust real-time face detection. So that is the breakthrough of their paper. And they are not the first one to developing the face detection algorithm. Okay, so now they also mentioned their failure cases. So from this image, you can find most of them are apparent faces. So it means if you change your orientation, so there are 3 different orientation: pitch, yaw, and roll. It means if you slightly tilt your head left or right, it won't work. If you change your orientation more than 45 degrees, it also doesn't work. So let's take a look. let's take a look result here and let's see. So this is my face. If I slightly rotate like this one, oh, it doesn't detect my face. Okay, if I change this way, okay, it also fails. So this is a limitation of the cascade of classifier. What is the reason? The reason is in their dataset, they don't have such training face images. Alright, okay. So it doesn't work. But however, let's take a look of the Blaze face. As you see, this is a part of the MediaPipe. Okay, let's take a look here. So this is face detection. Okay, so if I rotate my face, well, it works well. If I try this, okay, it still works well. Okay, so this is improvement from 2001 to 2019. Okay. Okay, so because this is it's a part of the open CV, it means every piece of code is public open sources. And so once I went to the GitHub code and I found something very interesting. There are 4 frontal face XML files. Okay, and there are also 2 cat faces files. And there's even 1 smile detector. Why I'm interested in smile detector? Because if you remember, N reported the smile detection algorithm, right? Okay, so there is also a smile detection algorithm. Which one is better? So one is deep face. Of course, deep face is much better than this heart-like feature detector. But let's see how well the heart-like feature detector will run. So okay, I should say, okay, I download the default frontal face algorithm. So because it's an XML file, so you can use any text editor to open it. So when I open it, I found it was released by Intel, and the resolution is also 24 by 24, the same as the paper. But however, there are only 25 stages. It means in the paper, it mentioned there are 38 stages or 38 layers. It means the number of weak classifier. But here, there are only 25. However, that is just the configuration. So I further take a look. For those layer index, there's 9, 16, 25, 25, 24. And the latest one, the number of weak classifiers 211, and then there are total 2,900 weak classifiers, but we don't know its training data. Okay, so since I found that there is a face smile detection, so I do a quick test how well or poor the smile detection work. So I download the code from this GitHub and slightly modify it to add smile detection. So here you can see also the smile detection is included in the GitHub file. I add the one. This is the upper body detection. Okay, and let's run it and see whether it can detect my smile. Yes, you can see there is a rectangle. Okay, and you can see there is some orange rectangle. It means there's a human upper body. So now let me see whether there is upper body here. No, it means the upper body part doesn't work. The performance is extremely poor. Okay. Okay, so what does it tell us? It means, yes, we have algorithm. The algorithm theoretically can detect any object. So that you can see here. The profile face, upper body, lower face, full body, smile, and the cat. But however, how about its performance? We don't know. The key point should be the performance. If it doesn't work well, then although there are some pre-trained models, we don't like to use it. But however, for face, frontal face, it works. I should say it is acceptable. The reason is human face is highly structured, and those features can work well for such image or such object. Okay. And so for human body, there is another famous algorithm called HUG, histogram of gradient. Okay, it is also mentioned in our textbook. But however, it was developed in 2005, also around 20 years ago. It is very famous because the performance is good for pedestrian. Okay, if we have time, let's talk about next time. If we have time, and if some of them use, then in your homework, then let's discuss that. Okay, now we still have a little time, so let's go back to our textbook. 2 weeks ago, we mentioned the architecture of networks. So this is a ResNet. It was a very, very famous net architecture, still used by many researchers today. And the ResNet means it learns the residue from its previous layer to its next layer. Okay, so there are several. So let's take a look. So this is a VGG19, and this is the ResNet 34. So you can see they learn residue from one layer to another layer. So the dashed line here means they need to do maximum pooling. So the resolution of those layers will be shrink down to half of that. Okay, so they cannot do residue here directly here. And this is the figure in our textbook. This means if you can choose very, very large network, for example, VGG19 or VGG16. You can also choose very small network. For example, this is the Google Net. And all right, so you can see for larger networks, you can generate a you can generate a certain level of accuracy. So this is the top 1 accuracy on the ImageNet. And you can see there is a frontal line from here. Okay, it means if you want to generate a better performance, you need to pay the cost. The cost usually is the number of parameters. And then MobileNet, ShuffleNet, they are also okay. Today we take a look at what the MobileNet is. MobileNet V1, V2, and V3. Let me say. Very few researchers use V3, and the reason is MobileNet V3 has some very specific or special operations. They may not be used by any kind of machine. Okay, and the MobileNet V4, it was just released in ECCV this year. Okay, it shows there is a very significant improvement over MobileNet V1 and V2. And the ShuffleNet is another attempt. Both of them want to develop a lightweight, quick network which can be executed on mobile devices. Okay. So let's look. This is the figure of MobileNet V4. So this is the performance of MobileNet V4. And V2 we just mentioned today is this purple line. Okay, So on different devices, for example, this is the Pixel 6. This is Samsung Galaxy S23. And this is iPhone 13. So for all these 6 types, MobileNet V4 generate a much better result than MobileNet V2. Okay. However, when I read the paper of MobileNet V4, I found this is so difficult. I cannot understand the details of those because they are experts for hardware. And then when they mention something, oh my God, what's that? Okay, I only get the concept. Okay, so you can see MobileNet V4 V2 was published around 7 years ago, and now it's MobileNet V4 during the 7 years. Okay, they developed a better architecture to run on mobile devices. Okay, this is also okay. So this figure was shown in our textbook because our textbook was written in 2022, 2 years ago. So here it also show the result of MobileNet V3. And here, this is a paper published in CCV this year. So this is a newer one. Okay, so I show both of them to I should say for a fair comparison because our authors it's impossible to show this 2 years ago. All right, and the next topic is how to visualize neural networks. So this is the unpooling and the deconvolutional neural network, as we mentioned 2 or 3 weeks ago. Okay, it means given a convolution layer, we use maximum pooling to subsample those feature maps. And if we can remember those locations, if we want to reconstruct the full resolutions, we can put those feature map intensities to those corresponding locations and do the convolution to reconstruct the image. Alright, so let's stop here. Okay. And do you have any questions? Alright, okay, no, thank you all, and let's continue that next week.